Great. So hi, everybody. So today we have a joint seminar between the AFMS, so that's the Australasian Fluid Mechanics Society, and the Shear Flow Seminar Series. Our speaker today is Dr. Petrônio Nogueira, who is a research fellow in the Laboratory for Turbulence Research in Aerospace and Combustion at Monash University. Petrônio completed his PhD at ITA Brazil in 2019, and his research interests include identification of coherent structures in turbulent flows, and I think he's going to be talking about some of that work today. So please take it away, Petrônio.
Thanks a lot for the introduction. So hi, everyone. So my name is Petrônio Nogueira. I'm research fellow here at Monash, and the title of this talk is Interaction between Coherent Structures in Turbulent Jets. And before we get started, I would like to acknowledge some of the research groups and funding agencies that supported me during this research. So first, I would like to thank CNPq, which is a funding agency from Brazil that basically supported me during my whole PhD. And I would also like to thank the Australian Research Council, which has been paying my salary for the past 2 years, basically. I would also like to thank these research groups here, and starting with Dr. Andrea Cavalieri and his group at ITA. He was my PhD supervisor and helped me a lot with these results. And also Professors Dan Henningson and Ardeshir Hanifi at ATH, Peter Jordan and Vincent Jonet at Institut de Prime, Professor Tim Colonius and Dr. Ethan Pickering at Caltech, Dr. Aaron Town and at the University of Michigan, and obviously Dr. Daniel Edgington Mitchell, who is my supervisor here at Monash. So today I'm going to talk about 3 different kinds of coherent structures in turbulent jets. And I would like to start with the most well-known, which are the wave packets. These wave packets are the key structure behind sound generation in turbulent jets. And this coherent structure was identified in the late 60s or early 70s by means of spatial correlations and by flow visualization, such as the one that we see right here in this picture from Crow and Champagne. In this kind of visualization, we can see some kind of structures starting to form quite close to the nozzle, and which are basically these puffs that we're seeing here in the turbulent field. So we see that these structures, they start small, they start to grow. Eventually, they will saturate here, and then they will decay eventually further downstream, which give us this final shape here. And that's basically why this structure has this name. This is a wave packet shape. But interestingly, this structure is connected to a linear stability mechanism, even though this is a turbulent flow, which is the Kelvin-Helmholtz instability, or the Kelvin-Helmholtz mode, that was studied by Mihalke in 64 or 65. And this structure is responsible for most of the sound radiated in the downstream direction for subsonic cases, and also for microwave radiation in supersonic cases. But these are not the only coherent structures in turbulent jets. We also have streaks, which are the most energetic structures for high azimuthal wave number. And streaks are kind of easy to spot in these flows if you take cross-plane slices of this jet. For example, for a Mach 0.4 turbulent jet, we have this slice here, which shows basically streamwise velocity fluctuations. And you can see quite clearly this kind of organization in the azimuthal direction. You can see blue, red, and etc. So the velocity field is quite organized in this position, and which suggests the presence of a quite coherent structure here, right? So if you perform some kind of modal decomposition of this turbulent flow in the whole turbulent field, such as SPOD, spectral proper orthogonal decomposition, then we can really identify this kind of elongated structures that we see here for m equals 10, for example, which compares quite well with what we see here in these slides, right? These structures are quite similar to very large scale motions in wall-bounded flows, and they basically hold the same overall characteristics, including the way they're generated. These structures are generated by the lift-up effect, in which these streamwise rolls or elongated vortices in the streamwise direction they generate these elongated streaks also in the streamwise direction. And this whole phenomenon is quite well captured by resolvent analysis. One interesting fact about streaks is that they inhabit at very low frequencies and high azimuthal wave numbers. And at this point, this map here proposed by Petrônio and co-authors 2020 is very useful, because here we can see where the lift-up mechanism is dominant, or where the streaks are dominant in the flow, which is basically high M and low Struhel, and where the Kelvin-Helmholtz instability, or the wave packet, is dominant, which is basically at low M's and higher Struhel numbers. So this map kind of shows these two coherent structures in the turbulent field of this jet, but we're not quite sure what's the effect of the interaction between these two structures. And we have no idea on how that will affect sound radiation, and everything else. Okay, and the last structure that I want to talk about here is the shock cell structure. And at this point of the talk, you may ask me, is it really a coherent structure? So if you remember your fluid mechanics course, you may remember that these shocks in the turbulent field, they arise due to this pressure mismatch at the nozzle. For example, if you have an underexpanded nozzle, we have an expansion wave here. These waves will be reflected at the central line. They will generate shocks after another reflection right here. And this sequences of reflections of the shocks and expansion waves will generate this quite coherent train of shock cells. And the interaction between the shock cells and the Kelvin-Helmholtz mode actually generates a quite sharp peak with high amplitude in the far field, which is basically associated with a resonance phenomenon known as screech. Okay, so this explanation is fine, kind of works for most applications, but I want to call attention about another work, and this is the work by Peck in the 50s. So basically, what he has done is basically to obtain the shock cell wave number directly from the Navier-Stokes operators using a vortex sheet model. So there's no really theta, beta, mac in his formulation, but it's just a vortex sheet and the adduction of this structure for very low frequencies. And other works kind of did the same afterwards. So we have this work by Tem and co-authors in 85, and Choi and Lele in 2001. And they showed basically the same thing. We have these two works kind of approximated this shock cell structure by a series of duct-like modes from the Navier-Stokes eigenspectrum. And in these works, the only input they needed was the equivalent ideally expanded mean flow. This is the main interaction. And in the end, the amplitude of the shock cell will be defined by the pressure mismatch at the nozzle plane. And this is basically why I'm saying that this is a coherent structure in the classic sense, because it may be obtained in exactly the same way as the other coherent structures that we know in these jets. So if you have a mean flow like this one highlighted in black here, we can perform a linear stability analysis or resolvent analysis and come up with the Kelvin-Helmholtz wave vector. Using the same mean flow, we can do some resolvent analysis and analyze the lift-up effect and obtain these streaks that we see here in blue. And in the same way, we can use the same mean flow and analyze these duct-like modes and obtain the shock cell structure that we're seeing here. So the method to obtain all these structures is very, very similar in this case. Okay, so this leads us to our objectives. And the first one here is to study the interaction between streaks and the Kelvin-Helmholtz vortices in a simple flow model. So I put these fancy figures here, but we're not really analyzing an actual jet, but a very simple flow model, which is a confined shear layer. And with that, we will isolate the main elements of the dynamics related to these important coherent structures in jets. And we'll try to understand how this interaction may affect sound generation and try to take advantage of that too. As a second objective, we'll study the interaction between the shock cell structure and the Kelvin-Helmholtz mode in actual round jets, and we use linear models for that. With that, we try to understand how the shock cells will change the stability characteristics of the flow and analyze the effect of the shocks in the wave packet development and show how this will affect sound radiation. Okay, so little word about simplified models. Simplified models can be very useful because they can offer a lot of insight about the turbulent dynamics in well-bounded flows especially. And a good example of that is Weyler flow, which was derived in 1997. Weyler flow is basically a well-bounded sinusoidal base flow, which was derived to study the self-sustaining process in well-bounded turbulence, which is given by this sketch here on the right. So basically we have streamwise vortices generating streaks by the lift-up effect. We have the breakdown of these streaks generating an x-dependent flow. And this x-dependent flow by some nonlinear interactions will regenerate these vortices. So this kind of sketch is very useful for well-bounded flows, but we have to remember that this flow is stable for all Reynolds numbers. So the question is, what about in free unstable shear flows like jets and shear layers? We have identified the lift up recently, so this part of the sketch is all right. We know that this is there, but we don't know if the x-dependent flow is just the Kelvin-Helmholtz or how the breakdown of the streaks will affect this Kelvin-Helmholtz mode and everything else, right? So the question is, can we adapt this sketch for free shear flows? And this is a very tricky problem, right? So in this problem, I had to ask the help of our honorary supervisor at ITA. And he's usually very helpful. Every time that we have a hard question, he would explain to us the maths in the textbooks, as you can see here. In more heated discussions, he would go to the whiteboard with him, and he would explain everything based on first principles and everything. And it was no different in this problem. So if you look at his face quite closely, all of a sudden the problem becomes a bit clearer. We can see these vortices around his eyes and nostrils, and also some streaks in between them, right? So his face is basically showing us a sample reduced order model in which we have streaks and Kelvin-Helmholtz modes kind of interacting. Okay, so jokes apart, and inspired by that, we are going to propose a simplified model quite similar to what Weyler did in 1997. And this is a simple Couette flow with a hyperbolic tangent body force, which leads to a laminar solution that shapes like a hyperbolic tangent, as you can see here in this figure on the right. And due to this permanent actuation and the behavior of this flow at low Reynolds number, this flow will be called permanently actuated, periodically unstable flow, or PAPU flow. And by definition, PAPU flow is a confined well-bounded shear flow with an inflection point. And this will lead to the appearance of Kelvin-Helmholtz-like vortices and streaks. This is already published, and in this paper we performed a characterization of this new flow by means of linear stability analysis and resolvent analysis, which allowed for a clear identification of the characteristics of these different structures and how they relate to the structures that we see in turbulent jets. But here in this presentation, we will focus on the second part of the paper, which is a direct numerical simulation, where all these structures will be present. So we designed the computational box to allow for a single Kelvin-Helmholtz mode and the most amplified streak with this permanent forcing. And in the end, this will simplify considerably the analysis of the interaction between these structures. And well, it may lead to further insight of what may be happening in actual turbulent jets. The results for low Reynolds number, they display a limit cycle, as we can see here in this energy spectrum as function of time. And this is basically the periodically unstable feature of PAPU flow. It involves clearly an interaction between streaks and rows, as shown here in blue and represented by this figure here, the Kelvin-Helmholtz vortices in yellow here, and the oblique waves shown here in green. So looking at a single period of this cycle, some features are quite clear, right? And this can be directly seen in the raw velocity fields. We don't need any kind of post-processing to look at this. For example, at this time here, we have a clear dominance of a positive streak at the center of the domain, as you can see by these arrows pointing forward. Afterwards, we have a cancellation of this streak right here, and the appearance of the vortices, as you can see by these arrows too. At this time, we have a dominance of a negative streak, so the streaks will change phase in this flow. And then we have the appearance of vortices again due to the cancellation of the streak. Note that here the vortices never change their phase. However, as can be induced by these tips that we're seeing here in the spectrum for oblique waves and streaks, these two structures change phase in every semi-period of the cycle. And these characteristics also remind us of some features of turbulent jets, right? In turbulent jets, the Kelvin-Helmholtz is subject to phase jumps, to amplitude variation and energy bursts due to this interaction between the unstable wave and the turbulence. And this phenomenon is called jitter, which affects reasonably the sound related by these structures. And this is similar to the amplitude variation that we're observing here for the Kelvin-Helmholtz mode, even though it's very, very organized and very organized and very simple. Also, streaks in well-bounded flows and also in jets, they often change phase as they travel downstream, following some kind of meandering motion or some kind of zigzag sometimes. And this is also similar to what we're seeing here too. We have these streaks are changing phase in every semi-period. So we have some elements of jitter and the meandering motions in this reduced order model too. Okay, so now we can detail this limit cycle dynamics a little bit. So analysis of the cycle shows that 5 modes are relevant. We have streaks that will be represented by S, vortices V, rhows R, oblique waves O, and the mean flow distortion M. And there are mainly 4 steps in this cycle, right? So in step 1, we have a linear stability of a streaky mean flow, explaining the periodic instability behavior of the flow. In step 2, we have streaks causing the phase reversal of oblique waves. At step 3, we have a nonlinear interaction between oblique waves and vortices generating new rhows. And finally, we have these new rhows killing existing streaks and generating new streaks with phase defined by the lift-up effect. And this will restart the cycle with a new streaky base flow. Okay, so let's start with step 1, right? The linear stability of a streaky mean flow from the DNS to explain the periodic instability. And before we really show this result, we need to do a quick review of linear stability analysis. So if you linearize the Navier-Stokes equations around a given 2D mean flow, we can obtain this eigenvalue problem shown here in this equation. And here, omega is the eigenvalue, Q is the eigenfunction, and basically all the disturbances will be written in this shape here, where Q, again, is the eigenfunction, right? That's basically the same Q here and here. So if you look at this equation and you look at the characteristics of the eigenvalue, so if the eigenvalue omega, the imaginary part of it, is positive, this flow will be temporarily unstable. This means that it will be exponentially amplified in time. If the imaginary part of omega is negative, then this flow is temporarily stable and all disturbances will be decaying in time, exponentially decaying in time. Which allows us to really analyze this first step, right? So we did that, we did a linear stability analysis each times of the flow with a streamwise average velocity field. At each streamwise average velocity field, we would have both the hyperbolic tangent profile and these streaks that we're seeing here. I'm just trying to highlight the streaks by subtracting the 10H profile. Okay, so for a given time that we have a positive streak, for example, in the middle of the domain, the unstable mode predicted by linear stability looks like this one that we're seeing here. Dominance of kz equals 0 here and here, 0 wave number in z, basically shows a dominance of vortices. But if we look at the center of the domain, we can see that we also have some wave number here, which is a sign of an oblique wave. And note that this region, this blue region at the center, is associated with this red region of the streak at the center of the domain. But instead, if we have a negative streak in the middle of the domain, as shown here, we can see that we have no changes in the phase of the vortices. We still have the same kind of phase here, but the phase of the oblique wave will change. So now we have blue here in the center of the domain. So the oblique wave will now have red, will be positive at the center of the domain. So this means that the phase of the streak defines the phase of the oblique wave that will be amplified by the flow at a given time. And this explains exactly why we observe these regions of growth and decay of the vortices shown in yellow, coupled with the regions of growth and decay of these oblique waves. So the streaky mean flow will support the growth of these two structures together, always together. And if we look at the growth rates of the unstable mode as function of time, we can see that times when the flow is unstable, it's predicted to be unstable by this linear stability analysis, matches very well with the times of growth of the vortices. And this basically explains this periodic instability behavior. The times when the flow is stable are also associated with times when the mean flow distortion is maximum, which leads to this decay of the vortices that we're seeing right here. Okay, so let's go to step 2. As mentioned earlier, this streaky mean flow will lead to the growth of vortices in oblique waves, and the phase of the oblique waves will be defined by the phase of the streaks. So for example, at this instant, the streaky mean flow will support the growth of oblique waves following this shape right here. This wave will grow and decay with the vortices in the flow, as you can see in this spectrum. But at this other instant, due to this phase shift of the streaks, the oblique wave supported by the flow has a phase shift too. So these two waves are now in phase opposition. And this explains why these oblique waves suffer a strong decay in the flow here and here, for example. So in summary, these oblique waves from a previous half cycle, shown here in blue, for example, are canceled due to the growth of a new oblique wave, shown here in red, that has a phase shift. So that's basically why we have this kind of behavior here. The next step of the cycle is the interaction between oblique waves and vortices, leading to a phase shift of the roles. And the first thing to notice here is in this step, is the alignment between the decay of oblique waves here and the roles computed from nonlinear terms of the Navier-Stokes equations, shown here by this dashed line. So these 2 points are basically quite well aligned in the time series. And this behavior occurs just before the decay of the roles in the velocity field, which is shown by this marked line here in blue too. So computing the nonlinear interaction between vortices and oblique waves, these two waves, the shape of the resulting velocity field looks like this. So these are basically rows in this direction, right? They are doing something like this. And those are basically rows that reinforce the lift-up effect that we see in the flow, right? So this is, again, the same streak that we saw before at this instant. But just after the cancellation of the oblique waves, these nonlinear rows will change orientation, as you can see here. So these nonlinear rows will now force new rows in the velocity field with a phase change, which basically explains the cancellation in the energy of the rows that we see here at this point. And we'll call these structures anti-rows. This formation of anti-rows will lead to a velocity field that has streaks and rows in an anti-lift-up configuration, as you can see here in this figure, which could not be maintained for a long time because that's basically opposed to the lift-up effect. So in the end, these new anti-rows will then generate anti-streaks or streaks with a phase change, which will cancel the previous streaks, as we can see here, and restore the leaf tuple configuration. And this will generate a new streaky mean flow that will restart the cycle. So now we can go back to our sketch of the self-sustaining process for wall-bounded flows and try to come up with something similar, right? And this is basically the summary of the cycle that we may compare with that sketch too. We're starting with a streaky mean flow. The stability of the flow will generate both oblique waves and vortices. And the nonlinear interaction between these two waves will generate anti-rows, or rows with a phase change. These anti-rows will force anti-streaks, or streaks with a phase change via the lift-up effect. And these anti-streaks will cancel the previous streaks, which is also associated with a high mean flow distortion, which leads to a vortex stabilization here. And then, well, after this whole process, everything restarts, now with anti-streaks and anti-rows. So it's basically like a dog chasing its own tail. Okay, so this leads us to our partial conclusions. Here we propose a new flow model, or Papu flow, to evaluate the interaction between coherent structures in a free shear flow. The main advantage of this model is that it allows for mode-by-mode analysis, exactly as in wall-bounded flows. We found that vortices, streaks, rows, oblique waves, and the mean flow distortion are the most important elements, and that these underlying dynamics can be explained by instability, lift-up, and nonlinear interactions. Overall, this model can be viewed as a minimal flow unit to study transition and turbulence in mixing layers and jets. And as a next step, we can, well, pump up a little bit more the Reynolds number and see how the actual turbulent Papu flow looks like. And we can also go back to the turbulent jet and try to evaluate if the same trends are also observed there. And for that, we can use even other linear stability models, such as Psc or Resolvent, to check if they lead to a similar behavior of stabilization, destabilization of vortices and streaks. Okay, so let's go to our second objective, which is to study the interaction between the shock cell structure and the Kelping Helm Smoldering round jets. And this is going to be a little bit trickier because here we need to develop a new formulation for linear stability analysis. So let's start from the basics. Let's start from the linearized Navier-Stokes equations in the frequency and azimuthal wave number domain, which is given by this equation right here. And following Tamentana 82, we can come up with a leading order approximation of a periodic shock cell as a cosine-like structure. So using that, we can propose a spatially periodic mean flow in this shape right here. So it's basically the regular mean flow we have for locally parallel stability analysis, summed with a cosine-like structure. And this structure has like an amplitude and a wave number. So in this problem, we will approximate UR as a hyperbolic tangent. A shock is the shock cell amplitude. K shock is a shock cell wave number, which can be obtained using Beck's approximation. And in the end, this new mean flow will be a surrogate for a mean flow with shock cells, just a first approximation. If we substitute this shape of the mean flow into our equations and linearize, we will end up with a system of equations that has this kind of periodicity, right? So all the coefficients of our equations, we have a lambda shock periodicity. And that allows us to use the flow K ansatz as reviewed by Herbert in '88. And using the flow K ansatz, we can write disturbances in this shape, where mu here is the flow K exponent, and Q hat will be represented as a Fourier series, as in this expression right here. So in the end, we can substitute this solution into the Navier-Stokes equations, and this allows us to write the whole system as a single eigenvalue problem, as in this shape right here. So if you're used to linear stability analysis, this is basically like the locally parallel problem. But now instead of having a wave number as an eigenvalue, we have the Floquet exponent as an eigenvalue. Okay, so let's talk a little bit about the characteristics of the solution and the method to get it. So as I mentioned earlier, the coefficient mu is the eigenvalue, which is connected to a wave number in X, the stringwise wave number. And as in spatial stability, if the imaginary part of mu is negative, this mode will be exponentially amplified in space if it's downstream traveling. All the operators are built using the mean flow quantities and discretizing the spatial derivatives using Chebyshev and Fourier. So this is a 2D problem, but it's quite a cheap 2D problem because you only have to discretize a single wavelength of the shock cell. So we just need this part of the domain to get a solution. So overall, the procedure to get this kind of solution is exactly the same as in spatial stability, but it's slightly more expensive. And one very interesting characteristics of this solution is that the solutions related to mu and mu plus an integer number of k shocks are identical just by reordering the Fourier coefficients of the eigenvector. And this is shown here in this figure in the bottom right. So here's a sample solution of SPLSA for 0 shock cell amplitude. And you see here, for example, several Kelvin-Helmholtz modes that are distant by k shock in wave number. And also several acoustic branches also distant by k shock and everything else. And these are basically shown in blue for the periodic linear stability analysis. In orange, yellow, and purple, we can see the results for the non-periodic linear stability shifted by an integer number of k shock. And basically, we can see that the SPLSA, or especially periodic problem, is doing exactly what it's supposed to be doing, right? You can see that all these modes find an equivalence to the SPLSA spectrum. And basically, all modes will now be found between 0 and k shock in the spectrum too. Okay, so we now have a new formulation to study the interaction between Kelvin-Helmholtz and shock cell structure. We have this SPLSA. So what can we do with it? Mainly two things, right? The first one is to evaluate the shock cell structure, the effect of the shock cell structure in each wave of the spectrum, such as the Kelvin-Helmholtz mode, in a perfectly periodic sense, at least. And like this one, like this figure that I'm showing here, this is just the Kelvin-Helmholtz and the effect of this modulation right here. Or we can also evaluate if different waves in the spectrum will interact due to this periodicity that we impose here in the problem. And this is shown here by this yellow figure here. So in here we can see several different modes. So for omega I equals 0, we have upstream waves right here in the real axis, and we have the Kelvin-Helmholtz mode right here. As we increase the imaginary part of the frequency using Briggs-Peirce analysis, for example, we can see that these modes start to get closer and closer to one another, which may be a sign of interaction in this flow. Okay, so as I mentioned earlier, we have these two waves. We have two waves that travel in different, in opposite directions in the flow in the same region of the spectrum. We have the downstream traveling wave, Kelvin-Helmholtz, and the upstream traveling mode, which is a discrete mode, in the same region of the spectrum. So will these modes interact? And the answer for this question is that depends. So if we increase omega I and vary Struve number and don't add any kind of shock cell amplitude, if shock cell amplitude is equal to 0, then these modes will cross path, but they won't interact. But if we include some shock cell amplitude, like 0.02, for example, these two modes will interact quite clearly here, forming a saddle point for omega I greater than 0. And this is a condition for absolute instability in this periodic problem, as derived by Brevdo and co-authors in 1996. So this suggests that this actually shows that in this periodic flow, you have an absolute instability, which leads the flow to behave like an oscillator. And the question is, so is this absolute instability related to what we see in experiments? Is this related to screech, to these sharp tones that we see in the far field? And the answer for that is yes. So basically, if you compare the frequency in which this saddle occurs for two sample cases here, we can see that they match very well with the speech frequency. So this is for example, for NPR equals to 2.1, nozzle pressure ratio equals to 2.1, and an axisymmetric mode. We see that the through of the saddle is 0.68, and the through of screech is 0.67. So these two values are pretty close. Again, for NPR equals to 2.4 and M equals 1, we have the through of the saddle equals to 0.4, roughly 0.44. And the through of screech is 0.42, as shown in the co-authors 2020. So basically, the frequency predicted by the absolute instability mechanism that we're seeing here matches quite well with what we see in experiments. But SPLSA also gives us more than that. It gives us the shapes of the modes close to this at this resonance condition. So if you compare the shapes of the modes at the saddle point with POD modes, for example, which basically represent the structure associated with resonance in these flows, we can see that we have a very good agreement. So we have, at least qualitative, we have a variation of the centerline velocity quite closely related to what we see in the SPLSA. We can see the presence of a standing wave right here, and the same in the POD mode. And this comparison is even better for the radial velocity here, in which you can see again the presence of a standing wave and the modulation quite strong across the inside of the jet, right? This comparison was for an axisymmetric mode for NPR equals to 2.1. But we also can compare with the other condition, right? For the other condition, for the M equals 1 mode. So for this condition, we don't have any POD modes or SPOD modes, but we do have POD modes for another condition that's also dominated by M equals 1, which is for an NPR equals to 3.4. So we can compare these two, keeping in mind that some wave numbers won't be directly comparable, but we can at least make a qualitative comparison. So for extreme noise velocity, we can see that the same qualitative behavior is observed across the shear layer with this kind of tilted structures here, and also here in the POD mode. And the comparison is even better for the vertical velocity. You can see this big shift behavior in the POD mode right here, which is a sign of a strong modulation, and the same kind of behavior for the SPLSA for NPR equals to 2.4 and N equals 1. So, and this is the final picture that I want to show about the absolute instability and this perfectly periodic model. And this is basically the prediction of the saddle frequencies for a range of operating conditions of under-expanded jets, and a comparison with the screech tones that we measured in the acoustic field. And as you can see here, basically all these frequencies are quite close to what we see in the experiments for the axisymmetric modes. So all this evidence that I showed here kind of suggests or points to the fact that screech actually occurs due to an absolute instability mechanism, which is triggered by the flow periodicity. And you can actually get that by just considering the shock size structure in our stability analysis. Okay, so we managed to look at the perfectly periodic case. But, well, can we use a similar formulation to study the downstream development of the Kelvin-Helmholtz mode? Can we check what's the effect of the shear layer development, for example? And yes, we can do something similar to what we've done before, but now with a spatially developing flow. So for a given flow condition, like an ideally expanded Mach number, a given temperature ratio, etc., we can do something like this. We can compute a first approximation for the shock cells using, for example, parabolized stability equations, and also with the shock-free mean flow. So this methodology is basically the same as the one derived by Choi and Lele in 2001. And as I mentioned in the introduction, the shock cells will be approximated by a series of Dirk-like modes. This is the first step, and then after that, we will take the solution and we linearize the Navier-Stokes equations around this quasi-periodic, slowly diverging mean flow. And this method, as the previous one, is based on the flow K ansatz, and it was first developed by Ren and co-authors in 2019, which was used to track secondary instabilities in boundary layers. Overall, this method is very close to very close to Psc, to the parabolized stability equations, and which renders the name parabolized flow key equations. So, and this is basically the last step. So in the last step, we compute the modulated wave packet using PFE. And by doing that, we can obtain wave packet shapes for each frequency and wave and azimuth the wave number. And we can validate this method using SPOD modes. And in the end, we can use these wave packets to define sound sources. We can use them to design control strategies or anything that you like. Okay, so let's start with Psc. So we start by writing the compressible Navier-Stokes equations linearized around a shock-free mean flow. That's one of the requirements of Psc, where Q here comprises all the flow fluctuations, right? We have velocities, pressure, and specific volume as function of frequency and azimuthal wave number. The Psc ansatz takes this shape. So we have a solution that has two main parts, a slowly varying part given by Q hat, and an oscillatory part given by gamma here. And gamma is also built using a slowly varying function of the streamwise wave number alpha. So recasting the solution into the Navier-Stokes equations and using the Leibniz rule, we can obtain this set of equations right here. And then we discretize the streamwise derivatives using first order implicit Euler method, which allows us to march the solution from the nozzle up to a given position downstream. And for revision of the Psc method, you can see the papers by Herbert and some other papers also that deal with this kind of method. So Psc was widely used in the analysis of coherent structures in jets because it can predict the shape of the wave packet as function of frequency and azimuthal wave number for a range of conditions, especially for shock-free mean flows. But something that wasn't really quite well explored is that the zero frequency Psc solution will lead to a first approximation of the shock cell structure, which is quite useful for us in some cases. So if you have a mean flow that looks like this, just by computing the zero frequency Psc, we can have a final solution that includes shocks, as you can see here, close to the inside of the jet, right? Inside of the shear layer. Okay, so this leads us to PFE, right? So, and we'll start here as in the previous case by defining a mean flow. But now this mean flow will include a first order approximation of a shock cell. So Q bar, our mean flow, will have this component, which is the shock-free mean flow, which was also used in Psc. And these other two terms here, which is one term and its complex conjugate. And this term here is basically built using the solution of zero frequency Psc for omega and m equals to 0. And gamma here is just the oscillatory part of that solution. And you should note here that I tried to isolate just the wave number part of the shock cell structure in gamma. And that will allow us to really use the flow K ansatz in the end. By assuming this slowly divergent quasi-periodic mean flow, we can now seek solutions in a slightly different shape, right? So now we have part of the solution that's related to the central wave number, as in classic Psc, which has wave number alpha 0. We have a second part of the solution, which is related to a modulation relative to minus alpha shock, minus the wave number of the shock. And we have a positive part of the modulation related to the sum of alpha 0 and alpha shock. And then you can include as many harmonics as you want, right? So we can include more and more modulations. We can have alpha 0 plus 2 alpha shock, 3 alpha shock, and etc. And then we substitute the solution into the linearized Navier-Stokes equations. For a single harmonic, the operators look like this. After some manipulation, we can gather out these terms associated with each modulation. And overall, the set of equations look like this, with this tri-diagonal structure for all these matrices, right? Note that here, the final solution is actually marched together. We have Q0 connected to Q minus 1, connected to Q plus 1, and this is marched all together in this method. So by simplifying these matrices in another operator notation, we can write the final equations as this form here, which has basically the same form or the same shape as Psc, and may be solved in exactly the same fashion with the same spatial margin. So some remarks about the method, just being super quickly here. Well, PFE, as I mentioned earlier, marches the central wave number coupled with the modulation wave numbers. So with that, we will obtain the modulated wave packet that results from the interaction between the Kelvin Helmholtz and the shock cell structure. For PSC, we have the initial solution of PSC is obtained from spatial linear stability analysis. And for PFE, we have the equivalent. This initial solution is obtained from a spatially periodic linear stability analysis. As in PSC, we can only march downstream traveling waves, so we can't really analyze screech. And actually, these upstream waves in the spectrum may destabilize this spatial march, and this leads to a minimum spatial step size for the PFE that's more restrictive than the ones used in PSC. For this reason, PFE is expected to work better in cases with high shock cell wave number, for example, in low Mach number under expanded jets, and just and at frequencies just before the screech tone. After you reach the screech tone and try to analyze frequencies higher than that, then the method is a little bit trickier to analyze. So overall, the solution of this method, the PFE, is a bit more expensive than PSC because we have a bunch of different harmonics being marched together, right? But it's way less expensive than any global method. So to get a solution here, just takes like a few minutes in my laptop, which is pretty nice. Okay, so going to the validation of these wave packets that we obtained from the method. Well, we need wave packets in the frequency domain to compare with, right? And for that, we use a large eddy simulation of a heated overexpanded jet, which was presented by Press and co-authors in 2017. This jet is screeching at through 0.26 in a precessing flapping mode, or m equals 1. It has a small shock cell wave number and the presence of a small Mach disk right here in this figure. And this data was generously provided by Dr. Guillaume Bress from Cascade Technologies. Here are some characteristics of the simulation. We have a nozzle temperature ratio of 2.5. The design Mach number is 1.5, and the Mach number, the ideally expanded Mach number of this jet is 1.35. So now that we have the simulation, the first step is to obtain the mean flow quantities. From that, we can perform an azimuthal decomposition of the flow fluctuations, around this mean. And as a third step, we can perform a spectral proper orthogonal decomposition, or SPOD, of the data. And this was done just for the pressure for this case. And this will allow us to extract the most energetic coherent structures in this jet. And here's the SPOD spectrum for this jet, for m equals 1. And the main characteristics of this result is the sharp peak that we see here in the spectrum. And that's basically related to the screech tone, to the resonance phenomenon. So since the PFE can't really deal with upstream waves, with the resonance, so we will avoid this region of the spectrum. And this region of the spectrum here is where PFE is expected to work better. So we have some sample cases right here, but we will also show some results for cases in this region of the spectrum. But don't expect a great agreement in this region. Okay, so to get PFE results, first we need an equivalent, ideally expanded mean flow. And we choose the model proposed by Sandham and Salgado in 2008. We have several coefficients in this mean flow model, and these were adjusted to the experimental data to provide a similar sonic line and a similar centerline velocity. But even though we did the best we could to match the mean flow for this case, we can still spot some differences in the shear layer thickness further downstream, as we can see here in this picture. And speaking about this picture, this is a comparison between the LES and the resulting shock cell structure from zero frequency PSC. And we can see that this PSC solution actually manages to capture some of the behavior of the shock cells. You can see that these regions of positive and negative velocity disturbances close to the center line is actually quite similar to what we see here in the LES. And we can actually see some kind of modulation also close to the shear layer. If you look at the centerline velocity, we can see that the comparison is even better. So the spacing of the shock cells is well captured until x over d equals 6, roughly. But after that, we have an amplitude mismatch, and the spacing is also kind of not captured in this region. And that's probably because of the choice of mean flow. Some fine details, such as the MAC disk, is also not captured. But overall, this is still a very good approximation, given that we're just using a linear model to predict shocks. Right? Okay, so let's go to the results then. But before showing the PFE results, I'll show you the PSC results using the same equivalent ideally expanded mean flow. So PSC actually does a good job here in this case. So it kind of captures the overall wave number, it captures the microwave radiation here and here, but it fails to capture the extended envelope for higher Struve number. And it also fails to capture the modulation of these wave packets, right? So if you look at the absolute value of the pressure for these cases, they are completely smooth. We don't have any of these structures that we see here in the LES, in the SPOD nodes. So that's one of the problems with PSC. It can't really deal with shocks. With PFE, we have a similar kind of result because it basically captures the overall wave number. It kind of captures a bit of the microwave radiation, but it's under-predicted for this case because we are using a large spatial step. We can't really predict any of the upstream waves, but it does capture some of these extended envelope for higher Struve number. And it actually does a good job in capturing the overall modulation, especially for lower Struve numbers, as predicted. Right? So this is where the PFE is expected to work better. So we can see that these lobes here are basically around the same positions. And even for the higher frequencies, we can see some of the modulation kind of comparable with what we see in the SPOD nodes. A better comparison may be seen when we take like slices of the jet, radial slices or streamwise slices. So for R over D equals 0.1, for example, quite close to the center line of the jet, we can see that the PSC again doesn't do a really good job in predicting the shape of the modulation, but PFE actually does a decent job in capturing the position of the peaks, like here, and even for cases when it's not really expected to work better. So we can see some of the peaks kind of aligned around the same regions of the flow, even for higher frequencies. If we go a little bit further in the radial direction, we can see that the agreement deteriorates. mainly because we don't have any upstream waves here. So all these modulation effect that's basically due to this interaction between upstream acoustic waves and the downstream Kelvin-Helmholtz or downstream acoustic waves, they won't be there. So in these cases, the PFE actually is comparable to the Psc results, except for this frequency here, in which we can see a quite good agreement for the PFE. So all the peaks here are basically around the same positions in the SPOD modes. Okay, so since the PFE can't really deal with upstream modes, one alternative here is to filter the SPOD modes to only consider positive wave numbers. And then we compare with the PFE reconstructed using only positive wave numbers. So that won't really remove all the effects of upstream waves, but it's a fair comparison considering that the PFE was basically made to capture this part of the modulation, right? And this reconstruction actually finds a good agreement too with the LES mode, with the SPOD modes, right? Again, we have a good agreement between the wave numbers that we see here, the PFE and the LES. And even for the modulation itself, right? So if you look at the absolute value, we can see that all these peaks are around the same positions too for most of these conditions, better for lowest true Helm number, a little bit worse for higher true Helm numbers. And again, if we compare it for this line quite close to the central line of the jet, we can see that the agreement kind of gets better for these jets too, especially for this case. But we can also see the same kind of agreement, so peaks aligned for all these regions of the jet. And again, this is way better than what we saw in the Psc results. Okay, so I promised you guys that I would talk a little bit about the effect on sound radiation, and we do have some preliminary results for that. So what I did here was to get these wave packets predicted from Psc and from PFE, integrated these wave packets in radius, and basically concentrated them in a line, and imposed this line in a cylindrical shell, so that we have this n=1 behavior of the wave packet. And with that, I defined a source term in the light year analogy. So that looks basically like this. We have a source term here. We will propagate this source term to the far field using a Green's function, using basically light year's analogy. And then we try to evaluate the sound radiated by this structure at given positions of the flow right here. And this is representative of what we're seeing here. So I'm showing results of the far field radiation of sources field using Psc and PFE for several conditions, right? For several true Helm numbers. Well, as expected, for all these frequencies, most of the sound is radiated downstream. And for lower frequencies, the inclusion of the shock cell doesn't really make a difference because, well, the radiation for this case is really, really strong downstream. But if you look at the other frequencies, you can see that the Psc solution shown here in blue is basically silent. So the difference between the downstream and the upstream radiation for these frequencies is roughly 30 or 50 dB. So that's a lot, right? But if instead we use a PFE solution as our source term, then we start to get a much stronger upstream sound radiation, and even for these mid-polar angles here too. And this suggests that this interaction between shock cells and the wave packet predicted by PFE may actually be responsible for the radiation pattern that you see in the far field for shock-containing jets. And this leads us to our conclusions. So here we studied two main methods. First one was SPLSA, which is basically a fundamental tool to analyze shock-containing jets, right? So with that, we managed to show that switch is an absolute instability phenomenon that can be captured by SPLSA. And this has consequences to other geometries too. So if we have elliptical jets, string jets, or rectangular jets, we have basically the same mechanism with the equivalent modes. And we also showed this new method called TFE, which is a method to predict and model modulated coherent structures in shock-containing jets. It has a very low computational cost, and with that we can obtain these modulated wave packets as function of frequency and wave number for basically any flow condition. We have a good agreement with coherent structures from the LES, especially considering the several modeling steps. So I'd like to remember here that we have a mean flow model that's not exactly as the one that we see in the LES. We have a shock cell approximation. We don't have any upstream waves in this model. And again, this is a linear approximation for a shock-containing jet. That's a bit of a stretch, right? And this kind of model can be used to build physics-inspired sound source models and to design control strategies, for example. And this is the final conclusion. Sorry if I advance a little bit on time, but if there's one message that I want you to take from this talk, is that the interaction between coherent structures in jets is an important component of the flow dynamics. And it may be really relevant for the studies of sound generation in jets. So local analyses are useful, but the consideration of other regions of the frequency and wave number spectrum in this linear analysis may lead to further insight about turbulent flows in general, may help us to understand what's really the physics here. And with that, I'd like to thank you and we'll take any questions now.
Great. So thank you, Petrônio. Oh, we've already got one question. So let's go ahead, Yuri, I think.
Yeah, thank you.
Got in quick.
Thanks a lot for a very interesting talk. You considered a lot of different kind of perturbations, but approximately 30 years ago, one more kind of instability in structures was found in underexpanded supersonic jets. These are Gertler instability, Gertler vortices. Within the first barrel of shock waves, due to curvature of mixing layer, this instability can appear. This was found experimentally and then supported by stability theory. Why don't you consider this kind of instability?
Because this formulation was basically written a few months ago. So the main focus of this formulation was first to evaluate this interaction with the Kelvin-Helmholtz vortices, because, well, they are one of the main structures responsible for sound generation, and my line of research is basically focused on that. But we haven't really analyzed the effect of these shock cell structures in other coherent structures and other instabilities of the flow. But it seems like a perfect tool to do that, because we can actually see this curvature of the shear layer in these reduced order models that we presented here, right? So yeah, we'll take that as a second step of this study.
Do you know about these results? I mean, Gertler instability. I can give you a reference if you want.
Yeah, I would love to, because I'm not super familiar with these Gertler vortices in underexpanded jets. But yeah, I would love to have a look. Thank you.
Okay.
Great. Thank you. And we have another person with their hand up. I think, go ahead. Oops. Oh, you're on mute. Sorry. Oh, sorry. You're on mute. Sorry.
Sorry. Okay. Thank you, Petrônio. Nice to see you again. And my question related to the your new method PFE and the Psc computations also doing. Are you doing an auxiliary condition to get the alpha for your waves or not?
The normalization to update the
auxiliary condition to get the alpha, the iterative value.
Sure. I'm doing exactly the same as in Psc. So I'm using the Q inner product between Q and du Q dx, the integral of that being equal to 0. That's okay. I haven't really had the chance to think about like a different normalization condition for this situation, but the Psc one seems to work very well.
Yeah. So my question is, then you have now 3 modes, correctly? that you're integrating at the same time.
Yeah.
So what is the relative amplitude of them towards each other? So you don't need to choose the relative amplitude of them?
No, we don't, because when we expand all the equations, everything comes together quite nicely. So all the relative amplitude of these different modes are actually given directly by the linear operators themselves. So we only have one free amplitude here, which is the amplitude of the final solution.
Okay, yeah, I get it. Yeah, yes. Okay, thank you very much.
Thank you. Nice to see you.
Thank you.
Great. There was a question in the chat that was asked kind of partway through the talk, which was just a clarifying question about, could you please talk about how the roles are different from the vortices?
Sure, that's actually a question that I get a lot, because there are just so many structures in this problem, right? So vortices, when I talk about vortices in Papu flow, is actually the Kelvin-Helmholtz vortices, or these vortices right here, vortices in the YZ direction. These are basically the equivalent to the wave packet in a turbulent jet. When I talk about rows, I'm talking about these rows that I mentioned here, these streamwise elongated rows that will generate the streaks in these flows. So it's just basically a difference between the orientation of these vortices, right? Kelvin-Helmholtz vortices they look like this, and the rows, they look like this.
Okay, thank you. We have another person with their hand up. Please, Saul, do you want to ask a question?
Sure.
Yeah, probably it's me. Can you hear me?
Yes.
Yeah.
Yeah. So in the very first part, you showed streaks, oblique waves, rows.
Mm-hmm.
It seems to me, and then secondary instability of streaks, or stability of streak. So it seems to me that they modulate on the same time scale, right? I thought the rows and streaks are longer structures and modulate more slowly than oblique waves. So
perfect. Yeah, that's a very good question. Thank you. One of the main differences between Papu flow and a real jet is that the phase velocity of the Kelvin-Helmholtz is equal to 0. So that's basically why these interactions occur around the same time scale, because these vortices will have a very slow time scale too, exactly as the streaks. That's why
my observation was right. So that in your case, the oblique waves and the streaks have the same length time scale, right?
Yeah, they have the same.
Yeah.
Yeah, they have the same time scale because the phase velocity of almost all waves here in this problem is basically 0, because we have a mean flow that looks like this, right? So if you take like the mean of this mean flow, we have a phase velocity that should be 0. So since the vortices and the oblique waves should grow together and they have this connection by the linear stability analysis, then the phase velocity of these two structures should be quite similar too, and they will be very close to the one from the streaks too.
Okay.
So yeah.
So when you do stability analysis, where was your mean flow? This osmosally dependent mean flow from?
From this simulation, actually. So
from direct numerical simulation.
Yeah. So instead of performing a temporal mean, a temporal average, I'm just doing a streamwise average to get the overall behavior. And
but
then use
in
that
that
as a
case, in that case, that mean flow has already included the back action of waves on the rows already, right? So
yeah, in some sense. But since I'm averaging everything, then the vortices will be canceled out because we're averaging X, and we only have the streaks in the end, the streaks and the actual mean flow.
Yeah. But okay, so something which worries me, honestly. Okay, I don't mean to be, to just to be critical for the sake of it.
No, that's okay.
If the streak and the modes involve on the time scale, so how can you freeze? So it seems you are doing instantaneous stability in time, right? So you freeze your streaks and at each instant and do the calculation. But the modes actually, the resulting modes do not involve at a shorter length scale. So there's a reason for concern, I would say.
Yeah, so this model has limitations, and we acknowledge that. But again, this is just a very first simplified model to try to understand the interaction between these waves. And the results are what they are, right? So this is a DNS, and you know that the dynamics that we're seeing here is actually what would the flow behave in a real case for this.
Yeah, I'm sure. Okay, so yeah, I can see the interesting result. I'm just saying there is this kind of very obvious question here. So if yeah, the base flow, the base streaky flow is involving at the same time scale as the total mode. So, but of course, you can back up the validity by comparison with DNS or other.
Yeah, we're still developing this model.
I'll ask another question. Sorry, I tend to take up more than fair share of my time of the time. In the shock cell case, right?
Sure.
The very first part, again, you took a simple profile. The jet flow is only radially dependent, and the shock cell has a constant amplitude in the axial direction. So any non-parallelism in the shock cell and in the base jet flow has been suppressed. And so you assume for periodicity in the axial direction, and that again is a very crude modeling.
Yeah, it is. It's exactly as the locally parallel linear stability analysis. And it has some limitations.
Of course, in the PSE, you are trying to take into account the actual variation.
Yeah, so the main objective of this first part and this perfectly periodic was to provide some kind of equivalent of the local linear stability analysis to a shock containing mean flow. So that's basically what we're doing here, and finding these equivalents, then we can extend all these models that we developed for shock-free mean flows to shock-containing mean flows. So we can use WKB, for example, or PSC, or one-way Navier-Stokes and everything else. So this is just the first step again of this project.
Okay, thank you.
Thank you.
Getting some good discussion in. So in the audience, are there any other questions coming in?
Well, I can carry on, but I have a few other questions, but I don't want to ask too much at this stage. So, okay, I'll wait for a while.
We'll wait for a little bit longer, and then we can go back. That would be fine. Just in case there's anyone with a burning question. Cool. It doesn't look like it. So maybe we'll finish up here, and then we can kind of stay on the line for more chat. So I think everyone can join me in thanking Petrônio once again for his excellent seminar. Thank you so much for providing this for our seminar series. It's been great. Thank you.
Thank you. It's a great opportunity. Thank you, guys.